right, so in the last two slides I gave you a little bit of an overview of how we actually do mesh refinement. Namely, we need to come up with some way of estimating how large, or let's say getting an indication of how large the error might be on every cell. And I introduced to you, for example, the Kelly error indicator that is fundamentally based on the interpolation error. And once you have evaluated something that for every cell gives you a number, how big you think the error might be on that cell, then that's the point where you have to decide, okay, so now that I have these numbers for all of the cells, which of the cells are the ones that are going to be refined and which do I want to coarsen? So what I want to do in this lecture is go a little bit beyond this. And that's going to be pretty mathematical, so there's going to be a lot of formulas. You will have to bear with me. It's not incredibly difficult, it's just a little bit technical to do this. And the idea really is that instead of, let's say, having a heuristic idea of how big the error is based on the estimation of, let's say, the interpolation error, I want to come up with something that is mathematically rigorous, something where I can say that, yes, this quantity is larger than or equal the error. And I want to do this ideally on a cell-by-cell basis in such a way that I can rigorously use this to refine the mesh. So the way I'm going to do this is through a process that is called a posteriori error estimates, which a posteriori means after the fact, and that means I can only do this after I have already computed the solution. The point of it all is that I will want to use the solution that I have computed. So let's say I have a mesh and I've computed UH on this mesh, my solution of the PDE, of the finite element approximation of this PDE. I've computed this on this mesh, and then I want to look at this solution and I want to say, okay, so it's a good approximation here, it's a bad approximation over here. So over there I need to refine, over here I can keep the mesh as it is or make it even coarser. So a posteriori means that I look at the solution that I have computed and use that in order to refine the mesh for the next step. So the steps that I will have to go through are, like I said, a little bit technical but not overly complicated. And I'm going to show this for you for the Laplace equation, because for that one it's really, I can do this in 10 or 15 slides. It's not terribly complicated, but something similar can be done for many other equations as well. So let me jump right into this. This is lecture 17.75, and I'm going to call this a posteriori error estimators. So if you recall, the adaptive mesh refinement always happened in a loop. I start with a solve step, and once I have the solution, I want to estimate for every cell how big the error is. Then I need to mark certain cells for refinement and possibly others for coarsening, and then I actually need to do the refinement. And so the purpose of this lecture is going to be exclusively on the estimate step. The previous lecture, of course, was on mark, and the solve is what we have done just throughout the rest of this course. Okay, so the estimate phase is, in essence, for every cell from K1 through Kn, I want to compute some quantity that I'm going to call eta that indicates to me how, let's say, worthwhile it is to refine this cell. So let's call this a refinement indicator. And we've seen in 17.25, 2 lectures ago, that a reasonable approach is to use the interpolation error as a quantity that we care about. And if you want to use the interpolation error, then you would naturally be led to something that is typically referred to as the Kelly indicator. And it works like this, that for every cell, so if we want to compute eta k, the refinement indicator for cell k, I need to integrate over the boundary of this cell. And the thing that I need to integrate over the boundary is the jump in the gradient. So how does the gradient change from this cell to the next cell? And that was easy to understand. Let's say if you had a piecewise linear, then the gradient is constant on every cell, but might be different on the neighboring cell. And if the gradient on this cell and the neighboring cell are very different, then presumably that means that the second derivative is large. and that's what gave us the interpolation error. So I need to compute the jump of the gradient from this cell to the next, need to take the absolute values, need to square it, integrate it over the boundary, take the square root, and then multiply it with an appropriate power of h. And in this case, that's the square root of the diameter of a cell. So conceptually, if this is not what we want to do, if we want to, let's say, not just base things on heuristics like the interpolation error, then maybe we can look towards the actual error. So let's say in an ideal world, what I would really like to do, of course, is I would like to define these refinement indicators based on the true error. And the true error on cell K could be something like the difference between the exact solution and the UH that I've computed, my discrete solution, and integrated over the cell, right? So this is the L2 norm here, which means that I have to take the integral of u minus UH squared and then take the square root of this. So there's, of course, a number of questions that I can ask. One would be, why do you want to do the L2 norm? Why is the L2 norm the appropriate norm to measure the error in? There are many other norms. Maybe I don't care about the L2 norm. Maybe I want to use the H1 norm or the L infinity norm. Or maybe I want to refine not based on let's say, an integral norm of the error, but maybe I care about just the point value. Maybe I want to know how much does cell K contribute to the error at one point in my solution. That's a reasonable question to ask. Why would the L2 norm or the H1 norm be special? Why is that the appropriate norm? And another question that I could ask, or that I should ask, is that, of course, if I define it like this, so if these are the refinement indicators that I want to use, I don't actually have u. I don't have the exact solution of my partial differential equation, because if I had it, I wouldn't need to solve the PDE with the finite element method, right? So the finite element method gives me an approximation, and I use this because typically I cannot exactly solve PDEs that I care about in practice. So how would I evaluate something like this? How would I evaluate u minus UH if I don't know u? And of course, that's exactly the point of this lecture, that we talk about these sort of things. And then a, let's say, slightly more philosophical question that's important to answer anyway is, let's say I have a cell with a large error. And my algorithm would say, okay, so even if let's assume that I could evaluate something like this. So I'm going to get a large eta k. And let's say there are other cells for which the error is small. So I would refine this cell based on the marking strategies that we've talked about in the previous lecture. Does mesh refinement actually guarantee that the overall error go down? Because if it doesn't, then maybe our whole strategy of only refining those cells with the largest errors is fatally flawed. Maybe it is not important that we refine the cells with the largest errors, but maybe there are other cells that need to be refined in order to make the error smaller. So it's an important question to ask and to answer. And I'm going to start with this. So I'm going to work myself through first question number 3. And then I'm going to spend a lot of slides on question number 2. And the question whether the L2 or the H1 norm is actually appropriate, that is something that I'm going to defer to the next lecture, because it leads to a, let's say, fundamentally different approach. There's let's say, an important question that we need to ask, and there's a lot of mathematics that we have to do, for which it would be very useful if we understood how it is actually done for something like the H1 norm of the error. So let me start with number 3. So does refining a cell decrease the overall error? And the answer to this question is not actually so obvious. So first, it depends on how you define the error. If you define the error as the L2 norm, for example, then the answer is not necessarily. If you define the error as the H1 norm of the error, then let's say for something like the Laplace equation I'm going to show you in a minute, that the error actually does decrease if I refine a cell. So it depends on the norm in which we measure the error. It also depends on the process. So if you define, for example, this UH as the interpolation of the exact solution, which of course in practice I can't do because I don't know the exact solution. I can't do an interpolation of something that I don't know. But if it was the interpolation, then yes, the error would in fact decrease because the interpolation is a purely local process. It happens on only one cell, right? The values on one cell the values of the interpolant only depend on that one cell and not on the values of the solution elsewhere. And so whether I refine a cell or let's say the error on a cell depends only on whether I do or do not refine this cell. The error on one cell does not depend on whether I refine another cell. So interpolation is a local process. But the Galerkin process, the Galerkin projection, so let's say which is the finite element solution, is not a local process. If I refine another cell, it's going to affect the local error on the cell that I currently am. So let's say if I refine a k prime somewhere, it's going to affect the error on k. And this process is typically referred to as error pollution, and it leads to strange effects. So if you have, for example, a reentrant corner, for example, the traditional L-shaped domain for where we test many things, then you will often find that in order to bring down the error, what you really need to do is refine only in the corner where the corner singularity is, and that it is enough to refine there to bring down the error in other parts of the domain as well. Right? So it's a little bit like if you switch off that big power plant that produces a lot of pollution, then you don't bring down the pollution only in the vicinity of the power plant, but you bring down the pollution everywhere as well. That's where that term comes from. So that's sort of the question number 3. And to discuss this in more concrete terms for the Laplace equation. So if you, for example, have a mesh T and you have a refinement that I'm going to call T plus, so it consists of the same cells plus a few more, or let's say I've replaced a few cells by their children. If you define the space VH on T and the space VH plus on T plus, then for the typical elements that we have, it's not very difficult to see that VH is a subspace of VH plus, right? So in essence, I just add a few more shape functions to the existing space in order to get VH plus. And these additional shape functions are the ones that are defined on the child cells. So if I were to define the error as the gradient of U minus UH, so that's the H1 semi-norm of the error, then I can show with not very much trouble that the error of the finite element solution turns out to be the minimum of, let's say, all possible choices here. So UH is that function that minimizes the error here. And the same is of course true for E plus, the error of U minus UH plus on this lightly refined mesh, that UH plus again is that function VH in the enriched space VH plus that minimizes the error. And so if you look at these two formulas, it's easy to see that the second one must be smaller than the first one because the expression is exactly the same, but I'm minimizing over a bigger set. VH plus is bigger than VH. That's the statement that I had here. So if I minimize over a bigger set, certainly the minimum cannot be worse, but it can be better, right? And so what I take away from this is that any kind of refinement of the mesh is going to decrease the energy norm error. So for the Laplace equation and the H1 norm error, that's easy to show. It is, like I mentioned before, not true if I had the L2 norm or if I had any other kind of equation for which it's not that easy. So for the Laplace equation, this particular step is easy to show. So, like I said, so it is not necessarily true for the L2 norm. What I care about in practice typically is if I say something like, okay, so let me refine 10% of the cells. Can I say something about the size of the error on the refined mesh compared to the size of the error on the previous mesh? So I would really like to show something of the following kind, that let's say E plus is less than or equal, let's say 0.9 times the error, okay? So that I have a factor reduction, and this factor must be strictly less than 1. So I would love to have a property like this, where I get a reduction, because then, let's say, if I could show something like this by refining 10% of the cells, then I would just refine 10% of the cells and get a 10% reduction in the error. And then I repeat this, and I repeat this, and I repeat this, and I can make that error as small as I want, right? If I always gain, let's say, a factor of 10%. So that is what we call convergence, that I get the error go to 0. Whereas if all I know is that the error is smaller than it previously was, then that does not guarantee convergence, because it might be that in the first refinement I gain 10%, and in the second refinement I gain only 1%, and in the third refinement I gain only 0.1% of the error. And you see that with this sort of strategy, the error will converge to something that is non-zero, right? And if the error converges to something non-zero, then that means that the solution itself does not converge. The discrete solution does not converge to the exact solution. So I would love to show a property like this with a theta less than 1. And the typical proofs that have been brought forward for these sort of things require a strategy that is called the Dörfler marking, after Willi Dörfler, is a professor in Germany. Is also sometimes referred to as bulk refinement. So the way this typically works is that you need to refine or mark a whole bunch of cells K, so that the sum of the error indicators on this cell is bigger or equal than a certain fraction of the sum of the indicators on all cells. Okay, so what that says is, for example, you need to refine those cells with the largest errors that, for example, make up 1/2 of the total error. And it might be that this is only a very small set of cells, but it's that the error on these cells together make up a sizable fraction of the overall error. And of course, if you choose alpha equals 1, then in essence, you want that the sum of the errors on the marked cells equals the sum of the errors on all cells. That would mean that you have to refine all cells. But the alpha needs to be bigger than 0, and oftentimes actually needs to be bigger than some other constant between 0 and 1. So that's what we call the Dörfler marking. It means that you need to have a sufficient number, you need to have a number of cells that you mark for refinement that together makes up a sufficient fraction of the total error, and then you can show convergence properties like this one here, for example. Okay, so with this question out of the way, let us come back to the question of how you could evaluate the true error. So if we really wanted to do something like this, that I wanted to do my refinement indicators based on the true error, so some kind of norm between the exact and the discrete solution on cell K, for example, then clearly I need to know what the exact solution is, or at least that's what one would naively expect, that I need to know the exact solution. So I don't know the exact solution, and I need to come up with mathematical ways to express the error on a cell in terms of quantities that I know. And the things that I know are only the discrete solution, is UH of x. And I think, let's say, when you first come to this topic, it seems like a miracle that I should be able to express the error between something unknown and something that I've computed only in terms of the thing that I know. That doesn't seem to make any sense. I certainly profess that I had that sort of feeling when I first heard about this. But we can do it, and I'm going to show you in the next several slides how to do this. And I will bring that term to bear again. So this is called a posteriori error estimation, because it only can be done after solving the problem for UH. Okay, so how do you do this? I want to show this to you for the Laplace equation, because for the Laplace equation it's actually, let's say, reasonably simple, but it can be done for many other equations as well. So for simplicity, let me assume that you want to solve minus Laplace u equals f, and you have 0 boundary conditions. Okay. So the weak formulation of this problem says, find me a u, a function in the function space h1 of, let's say, functions whose derivatives I can square integrate. Find a u so that gradient u times gradient v equals f times v for all possible test functions v in v, and that would be h10 in this case. And the discrete form, the discrete finite element formulation, would be find a UH, so the gradient UH times gradient VH is f times VH for all discrete test functions, VH in my finite element space VH. And for conforming finite element methods, we choose VH as a subset of V. And so, because VH is a subset of V, I can also test the first equation with these discrete test functions, right? So the first equation has to be true for all test functions. So in particular, it has to be true for the discrete test functions. So I can say gradient u gradient VH equals f times VH. That must be true for u to be the exact solution. And then I can subtract these two equations from each other, and I get something that is called Galerkin orthogonality. And that means that the gradient of the error, gradient of u minus UH, times gradient of VH must be equal to 0. We discussed this in one of the previous slides, or previous lectures already. So that's going to be the first step that I'm going to use in order to derive these a posteriori error estimators. So let me write down the error. The error in the H1 norm is going to be gradient of E integrated over the entire domain. So that's the total error in my finite element solution. And of course, the norm squared is exactly the scalar product between grad E and grad E. And because of Galerkin orthogonality, I know that grad E times grad something discrete is 0. So I can subtract something discrete over here. And what I'm going to choose is going to be the interpolant of the error. Okay? And that might look a little bit funny, but it really isn't. So E is just another H1 function, right? It's the difference between the exact solution and the discrete solution. It's some continuous function in H1 that I can certainly interpolate onto my finite element space. And that's what I'm going to call IHE, the interpolant of the error. Of course, I can't compute it. I don't know what E is, but conceptually I can do it, right? I should also notice that, so the error, this function E here is not necessarily 0 on the nodes. And so as a consequence, the interpolant of it onto my mesh is not 0 either, right? So the error might be anything. It's probably going to be small, which is not important for us here, but it is not 0 at the nodes of my finite element mesh, and consequently the interpolant is typically not 0 at the nodes either. Okay, so I have this expression here, and then I'm going to write, so this, when I say parenthesis grad E times grad something over omega, that's of course the integral over the entire omega, and I can split this integral up into a sum over cells and then just integrate on the cells. And on each cell, I'm going to integrate this by parts. So I'm going to integrate, I'm going to move the gradient from here to over here. That gives me minus divergence if I integrate by parts. So on every cell, I get minus Laplace E times E minus IHE on the cell. And of course, integrating by parts always gives me boundary terms. And the boundary terms goes over the boundary of the cell and it has the following form: n times the gradient of E times E minus IHE. So let me look at this for a second. So the Laplacian, minus Laplacian of E, that's minus Laplacian of U minus UH. So I just multiply this out. So it's minus Laplace U plus Laplace UH. And of course, I know that minus Laplace U, that U is the solution of the exact differential equation. So I know that minus Laplace U is F. So I have F plus Laplace UH. And this is what I'm going to call the residual. So residual means something that remains. Of course, if UH was the exact solution, right? So if I could find the exact solution somehow, then the residual would be 0, because F plus Laplace U is 0, but F plus Laplace UH is typically not. So in this context, one of the things that's important to notice is if you think of UH, for example, as a piecewise linear function, then the gradient is constant on every cell, and I cannot take the second derivatives of it because that would be singular at the interfaces between cells, right? So this is why I needed to first break the integral over omega into integrals over the cells. On every cell, Laplace E, or Laplace UH, is well defined. So on every cell, I can do this integral, whereas I cannot do this on the entire domain because Laplace UH is not defined at the interfaces between cells because, like I said, the second derivative of a piecewise linear function does not exist at the points where the function has a kink. Okay, so the second part that I want to discuss is this E minus IHE. If I look at this on the boundary, so E is of course U minus UH, and the interpolant would be IHU minus IHUH. So if I take a discrete function and I interpolate, of course I get back the discrete function. So I have U minus UH minus IHU plus UH, so the UH's cancel, okay? And then if I restrict this to the boundary, then I have U on the boundary, which I have assumed is 0. That's my boundary values for the equation that I wanted to solve. And of course, if I interpolate on the boundary something that is 0, I'm going to get 0 as well. So the reality is that in all of these integrals over here, these integrals over the faces, they really are only over the interior faces, right? Because on all of the faces that lie on the boundary of the domain, these terms would be 0. The second factor in this integral is 0. All right, so if I put this in here, then I have that the exact error integrated over the domain is a sum over cells, F plus Laplace UH times E minus IHE, integrated over every cell, plus n times gradient E times E minus IHE on only the interior faces. So what I would like to do is I would like to keep looking at the second term here. So what we're doing here is we loop over all of the cells, and on every cell I'm going to integrate over the interior faces. And if you think about this, that means that I'm going to visit every face twice, right? So if I have neighboring cells k and k prime, then I'm going to integrate from cell k. Let's say this is a triangle or a square cell, k and my k prime. I'm going to integrate over the boundary here, so I'm going to visit this face here. But then I have a sum over all of the cells, so eventually I'm going to visit the cell over here, my k prime, and I'm going to integrate over the boundary. I'm again going to integrate over this face here. So every face I'm going to visit twice. And the formula says that on every cell, I'm going to integrate n times the gradient of k. So that would be the gradient of UH. The gradient of UH on this cell times the normal vector. So the gradient is the vector times the normal vector, that's a scalar. And I'm going to do the same thing over here, where again, I'm going to consider the gradient of UH times the normal vector. But the normal vector from this cell is exactly the opposite from the normal vector on this cell. And so what I would like to do, instead of visiting this cell and this face once and only computing the contributions here, and then going to this cell and computing contributions on this face. Every time I visit one cell, I would like to compute 1/2 of the contribution from this cell plus 1/2 of the contribution from the neighboring cell. And then I go over here and I do 1/2 of the contribution of this cell plus 1/2 of my neighboring cell. This is of course exactly the same, right? I just exchanged 1/2 from one term in the sum to the other term in the sum, right? That's sort of the idea here. So in formulas, this looks like this. So my sum of cells over the interior faces, I'm going to write this as the sum of cells of the contribution from cell K plus 1/2 of the contribution from the neighboring cell, right? That's exactly the same thing. I just added these contributions at different times. And then I need to remember that the normal vector on cell K prime is minus the normal vector on cell K, okay? So where I have a plus here, I can replace nk prime by minus nk, then I get a negative sign here. This term, e minus ihe, that remains the same because e is a continuous function, or let's say it's an h1 function. You can think of it as continuous. The interpolant is also continuous, so whether I evaluate this from k or from k prime is going to be exactly the same, okay? But it's important to remember that the gradient of E is not a continuous function, right? Because the gradient of UH is not a continuous function. UH is a piecewise linear, it's continuous, so the gradient is, let's say, on triangles, piecewise constant. The gradient on cell K is not the same as the gradient on cell K prime, even though we integrate over the interface between these two cells. All right, so if I put this together with the negative sign that I get here, so this whole boundary term over the faces turns out to be a sum over all of the cells, still a sum over all of the faces of this cell, 1/2 times nk times the gradient on this cell minus the gradient on the neighboring cell, evaluated at the interface. All right, so let's keep looking at this. So if I say gradient E on K minus gradient E on K prime, let me write out E as U minus UH. Okay, so gradient U on K minus gradient UH on K minus gradient U on K prime minus gradient UH on K prime. Okay, so we know that the solution of the exact solution of the Laplace equation is smooth. So that means that it in the interior typically does not have kinks, and I need to have some regularity assumptions that the right-hand side, for example, has certain properties, but let me assume that my right-hand side f has certain properties. Then I know that u, for example, is twice differentiable, and if it is twice differentiable, then at one location, at the interface between two cells, the gradient of the solution from the left and the gradient of the solution from the right at that interface is going to be the same for the exact continuous solution. So the difference between these is 0. But from a piecewise linear solution UH, that's not going to be the case. The gradient from the left and the gradient from the right are going to be different. And we've already introduced a notation with these square brackets. That's going to be what I call the jump, okay, the jump in the gradient. So what I really have here is that the gradient of E on K minus the gradient of E on K prime, that's the jump in the gradient. So I put this back in there, and I still have an equality. Where did it go here? Here I still have an equality that the total error here equals a sum over all of the cells of the cell residual, f plus Laplace UH times E minus IHE on the cell, minus 1/2 of this jump residual times E minus IHE integrated over the faces of the cell, or over the interior faces of the cell. So that's an equality still, it's exactly true. What you've seen, of course, is that at least in these first two factors, here and here, I've gotten rid of the exact solution. Okay, I still have the exact solution in here. I cannot evaluate this formula as is because I don't know what E is. In order to compute E, I need to have the exact solution U. So I will have to keep working on this, but at least in these residuals, I've gotten rid of it. So what I'm going to do is I'm going to use the Cauchy-Schwarz inequality on the cell and the phase integrals. And so the Cauchy-Schwarz inequality says that the integral of f of x times g of x for any function f of x, that is in L2, for example, is less than or equal the norm of f times the norm of g. So if I do this here, now this is an inequality. I get that this integral here, this one here, is less than or equal the integral of f plus Laplace UH on k times e minus IHE on k, plus 1/2 of the norm of my jump residual times the norm of e minus IHE on the interior faces. And so this is how this looks now. Now I need to think a little bit. So the fact that I have e minus IHE, the fact that this is actually the error here, is not going to matter to me. The way I'm going to see this is that e is just some h1 function. And we know that if I subtract from an h1 function the interpolant, IHE, then that must be small, and in particular it must be proportional to the mesh size. Okay, that's just a fundamental interpolation estimate. Take an h1 function, subtract from it the interpolant, you're going to get something that is proportional to hk times the gradient of E on the cell. And I can do similar arguments if I just have a function and I subtract from it its interpolant and I measure this on a face. I'm also going to get something small that is going to be like this here, the h to the 1/2. So the mesh size to the 1/2 times the gradient. And this 1/2, just like the power of h here, is really just something that comes from the domain over which I integrate. So I have these two estimates, and I can, you see that on the right-hand side I have the gradient of E, and that's going to be really convenient because I get a factor of gradient of E here, but of course over here I had the gradient of E squared. So I need to work a little bit still because I have this only on cell K, whereas I need it on omega, but we're almost there. So I want to cancel these on both sides. And the way I do this, so you see the estimate in the top line here. I'm going to pull this gradient of E out of the sum. Okay, so I'm going to get this as a common factor. And then I'm going to use the Cauchy-Schwarz inequality that for vectors this time, that says if I have, or for sums, if I have a sum xi, yi, then this is less than or equal the sum of xi squared and the square root of this times the sum of the yi squared and the square root of this. That's really just the dot product of vector x times y is less than the length of x times the length of y, right? But I'm going to apply this to the sum that I have over here. So I have a sum over all cells k, and if I apply this, then I'm going to get something like this. So sum over the cell residual plus the edge residual squared, and the square root of the sum times the sum over the cells times the gradient of E on the cell k squared to the 1/2. Well, that turns out to be exactly the gradient of E integrated, or the square of that integrated over the entire domain square root. So that's the h1 semi-norm of the error, right? That's really convenient because that's what I have on the left side as well, and so I can cancel one of these factors. Before I move on, one of the things that I should have pointed out in the previous slide, in this interpolation estimate there is a constant c here that has something to do with the polynomial degree of my finite element, for example, has something to do with the shape of the cells, and so on and so forth. I can quantify this, so I can typically compute upper bounds for this constant. But I want to point out that there is a constant here that we have to keep track that comes out of these interpolation estimates. Okay, so if I put this all together, I have the constant over here times the sum of the residual squared and 1/2, and then I have the norm of the error in the H1 semi-norm. So if I'm going to divide both sides by gradient of E integrated over omega, I'm going to get this thing here. So I have that the error, gradient of E integrated over omega, is this constant sum over k, over the cells k, times the cell residuals times the phase residuals integrated over the cells and the phases, multiplied with appropriate powers of h to the 1/2. Lo and behold, you will realize that everything on the right-hand side is known to me, right? I can evaluate f, I can evaluate UH, I know what my mesh size is, for example. I can approximate these integrals through quadrature, for example. So everything on the right-hand side is, in principle, computable, okay, with the possible exception of this constant c here that I don't know yet. But that's the spirit of a posteriori error estimates, that I end up with something that is computable on the right-hand side. Okay, so I can evaluate this. I can say, yes, the error on cell k is less than or equal, or let's say the contribution of cell k to the overall error is less than or equal what I have here in these parentheses. The last reformulation that I want to do is, let me take the previous formula and just square both sides. Then I have that the error squared over here is less than or equal to the sum of these terms here in parentheses. And what is in the parentheses, that's what I'm going to call eta k. So that's something like my error indicator, or my so it's the total error is not the sum of these, but the square of the error is less than or equal to the sum of the squares of these indicators. We call them residual-based error estimators because they are based on the cell residual f plus Laplace UH and the jump residual n dot gradient u, or n dot the jump of gradient u. That's what I'm going to use for mesh refinement then, right? These are computable quantities on every cell that I'm going to use for mesh refinement. So I want to add a few comments to this. So the first note is if I forgot about that first factor. So if I just drop the cell residual here, for example, then what you have here is, of course, exactly the Kelly error estimator, or the Kelly refinement indicator that we've talked about in the previous two lectures. So there is a good reason for this. We can show mathematically it's a really awkward computation. I certainly don't want to repeat this here, but I can show that for odd polynomial degrees, the jump term here is has a lower convergence order than this one. So this one, for example, would go something like h squared, and this one would go like only h. So if the mesh size is small enough, this term is going to dominate, and this term can be neglected. And so for odd polynomial degrees, it does make sense to only consider this term here, and that would be exactly the Kelly indicator. I should caution that for even polynomial degrees, that is not the case. So for even polynomial degrees, it turns out that this term is the dominant one over this one here. So for even polynomial degrees, strictly speaking, this inequality is not going to be true. This one here is going to have, let's say, order h to the 3, and we've neglected a term that would be h squared. I've neglected the dominant term. That is mathematically certainly not reasonable, but it turns out that, let's say, the Kelly indicator also yields pretty darn good meshes for even polynomial degrees. So even though it is mathematically, strictly speaking, not allowed to do this, from a pragmatic perspective, if all you care about is good meshes, it still makes sense. Okay, so I'm going to wrap this lecture up with 4 conclusions. So the first one, it is possible to bound the unknown error exclusively in terms of the known computed solution. That's exactly what I showed you, right? That for the Laplace equation, I can bound the unknown error in terms of only quantities that I can compute, namely the UH. The F is given, the jump of UH is computable, the Laplacian of UH is computable, and for the C, at least I have some sort of upper bound. We can do very similar things for many, many other equations. So if your goal is not to solve the Laplace equation, but the Stokes equation, or the Navier-Stokes equation, or the Helmholtz equation, or the advection diffusion equation, typically you can derive some kind of error estimate for this as well, where you have the residual. So for the advection equation, for example, you would not have F plus Laplace UH, but you would have something like F plus beta dot gradient UH. And for the Stokes equation, you would have, let's say, F plus Laplace UH minus gradient P, and then you would have another residual of the form divergence UH, right? So all of the residuals of all of these equations would enter somewhere, and then typically you also have these jump terms there. Let's say every time you have a second order derivative in your equation, you're going to get a jump term. So we can do similar things for many other equations as well. Secondly, so if you go back to where this constant came from here, this the C that we have here, that in the case that I showed you for the Laplace equation came out of these interpolation estimates. And we can compute upper bounds for this. So for let's say triangles, for linear triangles, we can show that the C is something like it is bounded by, something that has to do with the interior angle of the worst triangle in the mesh. Let's say the smallest and the largest interior angle of the worst cell in the mesh. And there is a very, very long paper, very technical, by Karsten Carstensen from, I don't know, the late 90s, I think, in which he really tries to estimate this constant accurately. Very technical. And he comes up with an estimate, I think, on the order of 60. We know from practical experience that when we compute things on a finite element mesh, we can ask questions. I give you a function u, and you subtract from it the interpolant on the mesh. How big is that difference? So we can do an estimate of this constant for practical cases. And we know that that is roughly 0.1 whenever we try these sort of things. So the fact that Carstensen in his paper estimates that it is less than or equal 60, for example, is a heroic effort, but it is far off from reality, simply because when you do these estimates, you have to take into account the worst case situations, and these worst case situations don't typically seem to happen, and so on and so forth. So that's sort of where the problem comes from, that in reality, in these estimates, we have these constants C that we know we can bound somehow. We have an upper bound, so that means that if we can evaluate the right-hand side, we know it's going to be bigger than the actual error, but it's typically a huge overestimate. So from a practical perspective, the fact that we can evaluate the right-hand side is useful in order to define where are the cells with the big errors and where are the cells with the small errors, so that we can define which cells we want to refine. But from a practical perspective, because we don't have a good handle on this constant C, we can't really typically say that, you build a bridge and the deflection at this point is going to be less than 0.1 millimeters. What the estimate is going to say is the deflection is going to be less than 60 millimeters, for example, or 600 millimeters, when the real error is only 1 millimeter. So the estimate is far above the true error. And that's because we don't have a particularly good handle for this constant C. And I should also say that the Laplace equation is one of the most trivial cases, and the only occurrence where this constant C came from was from the interpolation estimates. If you had other equations, the advection equation, the Stokes equation, and so on and so forth, we would have had to do many other estimates in the process. So there would be a stability constant, there would be maybe a trace inequality, maybe something. Every time you get one of these estimates, you're going to get a constant that in practice you can estimate from above. So you have an upper bound for this constant, and that means that if you put the upper bound into the error estimate, you will be able to guarantee that the error is less than something. But the something is going to be far, far bigger than the actual error, because the constants that appear in there are poorly known. And the more of these estimates you have, in addition to just the interpolation estimates, the worse these constants become. So from a practical perspective, this constant C really is a nuisance. Like I said, if you just forget about the constant, you can still, of course, take everything that's in parentheses here, and you can call this eta k. You will not have that the error is bounded by just the sum of these eta k squares, right? There is still this constant C. But from a practical perspective, the eta k's at least are computable, and they yield good meshes. So if you want to use these error estimates for mesh refinement, it's a very useful strategy. The last conclusion that I have here goes back to the first question that I asked, namely, why would I care about the H1 norm of the error? And for the Laplace equation, the H1 norm of the error is the gradient of E squared, or the gradient of E squared integrated over the domain and then the square root of it. So strictly speaking, it's the H1 semi-norm, but we know that with zero boundary values, the H1 semi-norm is also a norm. So why would that be the appropriate norm to consider? So why do I want to derive error estimates where I say that the gradient of E, the norm of the gradient of E, is less than or equal to something? So sometimes we actually do care about this. So for the Laplace equation, the gradient norm has the meaning of an energy. So if you think about the Laplace equation as something that describes, let's say, the deflection of a membrane, then the energy that is stored in this membrane is proportional to the gradient of the displacement squared. Similarly, if you were to consider something like electromagnetics, oftentimes the energy that is stored in something is proportional to the gradient of the electric field, the gradient of the magnetic field, these sort of things. So there is physical reason why I would care about the gradient of the error, because it is something that has physical meaning to the system under consideration. But oftentimes, I don't actually care about this. So let's say if I want to build a bridge, and I solve the equations of linear elasticity that would compute, let's say, if I put a certain force on the bridge, how much does the bridge deflect? Then what I really care typically is how big are the stresses in my bridge? And in particular, what is the biggest stress? Because that is going to be the place that breaks first. And what I need to make sure from a practical perspective is not that some energy error is less than something, but I need to make sure that the biggest stress in my bridge is less than or equal the breaking stress of concrete, for example, or steel. So in cases like this, and that happens quite frequently in the engineering sciences, I don't care about the energy norm. I don't care about the H1 norm of the error. What I really care about is a different quantity. I would like to know what is the difference between the exact maximum stress for the solution that, of course, I can't compute of the partial differential equation minus the maximum stress in my finite element solution, right? That is the quantity that I care about. So we typically say this is a functional. It is a functional of u minus UH, and the norm is, of course, just another functional, right? But I care about, let's say, physically engineering motivated functionals much more in practice than I care about the H1 semi-norm. And so sometime in the late 90s, people came around and asked questions, okay, so if that's what you care about, if you don't care about the energy norm or the H1 norm, but about functionals of the solution, are there ways that I can estimate the error in this as well? And there are ways to do this that we today call goal-oriented or error estimates. Goal-oriented because I have a goal function or some quantity that I care about from a physical perspective. Goal-oriented error estimates try to quantify the error with respect to a goal functional as opposed to the H1 norm or some other norm of the error. And there are ways to do this as well. And I'll come back to that in probably the next lecture then. So with that, I'll leave it. I hope you got to see that there are really ways how I can quantify the error between the unknown exact solution and the known finite element solution only in terms of things that are known, which is a little bit remarkable. That leads to these a posteriori error estimates, and that's going to be one way by which we can refine meshes. And then in the next lecture, I'll come back to how do we extend this to the case of goal functionals.